I've mentioned before that if you tell somebody that you study algorithms or that you're taking an algorithms course, there are certain topics that they're just going to assume that you have to know about. There are certain things that all of society assumes that everybody who studies algorithms, no matter where you take your algorithms course or what algorithms book you read, has to know about. One of them, as I said last time, seems to be self-balancing binary search trees. Now, obviously, we don't expect everybody who's taken an algorithms course to know every detail about self-balancing binary search trees, but it is one of those subjects where, I don't know, we expect people that have studied algorithms to have some kind of informed opinion on. And maybe that's because dictionaries are sort of a big deal, because searching problems are everywhere, and there's something that everybody needs to solve, so not just people that study algorithms. And I mentioned last time that there are lots of dictionary implementations out there that are based on self-balancing binary search trees, and that's one reason, I guess, that when you study algorithms, you have to know a thing or two about self-balancing binary search trees. But there are also dictionaries out there that aren't based on those. And the data structure that a lot of dictionaries are based on is something called a hash table. And I said last time that self-balancing binary search trees are a big deal and they're found everywhere, but also hash tables are a big deal and are found everywhere. And in a typical standard library, so if you look at the Java standard library or the C++ standard library, you will find data structures that implement dictionaries using both things. So using self-balancing binary search trees, probably a red-black tree on the one hand, and using hash tables on the other. So hash tables are a pretty big deal, and they're going to give us an opportunity to talk about a few things that have sort of been hiding in the background so far in this course. So hash tables, and in general the study of hashing schemes, requires some knowledge that's a bit out of scope for us. So it turns out the study of hashing overlaps a lot with the study of things like probabilities and randomized algorithms. And in fact, hashing is used far beyond the study of hash tables as a data structure. You might encounter applications of hashing or cryptographic hash functions if you study cryptography or any other crypto stuff, because hashing is sort of a big deal in that subfield as well. We're going to constrain ourselves pretty tightly just to talking about hashing as it is needed for the hash table data structure, which is used to implement a dictionary. But first, for some reason, I want to talk about a combinatorics problem. So I propose that in any group of 8 people, there must be at least 2 of them whose birthday is going to fall on the same day of the week this year in 2025. Now, before anybody tries anything funny, 2025 is not a leap year. I've got nothing else up my sleeve here. I've deliberately chosen this problem that mentions birthdays because it calls to mind something called the birthday paradox, which is the property that you don't actually need that large of a group of people before it's extremely likely that 2 of them actually have the same birthday. That is, their birthday falls on the same day of the year. But this claim has nothing to do with that. This claim is also about birthdays. It's just about days of the week. All I'm saying is if you give me any group of 8 people selected from anywhere, there will be at least 2 of them whose birthday falls on the same day of the week. So for example, maybe it's Monday. It could be that there's one person with a birthday on a Monday in February and one person whose birthday falls on Monday in July. It doesn't have to be the same month or the same day of the month, but it's the same day of the week. But it might not be Monday. It might be Tuesday, it might be Wednesday. It could be that all 8 of them have their birthday on a Wednesday this year. I don't know. All I know is that at least 2 of them have their birthday on the same day of the week. Take a minute to think about this claim and think about how you might write a proof of it. I'll assume you pause the video to do that. What's weird about this is once you have a chance to let it sink in, it sort of seems obvious almost. And I'll show a proof that I've written, but really, even I sort of fell into that habit of, on an exam where you have a question that seems to require a long answer, like you've got all this space to write your proof, and it just seems like the answer you come up with is a little bit too short, and you get nervous. You're like, did I miss the point? Is there something obvious that I'm missing? So actually, even I fell into that here, and I think this proof is probably at least 1 sentence too long. I've had to write some extra information to make myself feel better that I've given you your money's worth, that I've actually provided a legitimate proof. So here's my proof. Everybody in the group will have a birthday. This is a reasonable, I guess not quite a mathematical assumption, but a reasonable assumption that if we're talking about people, that they have been born, and that once they have been born, they have a birthday, and that birthday occurs every year. I'm not going to worry about people whose birthday is on February 29th. I don't know what they do in 2025. That must be tough for them. Sorry if you're one of those people, but I'm not. So unfortunately, I have no compassion whatsoever for that situation. Everybody in the group will have a birthday in 2025, and everybody's birthday must fall on a day. It must fall on one of the 7 days of the week. There are only 7 days in a week. This is me trying to pad the proof out a bit. And therefore, because there are 8 different birthdays and only 7 days of the week to fit them into, well, I'm afraid at least 2 people are going to have to share. So even if I try and distribute the first 7 people, giving each of them their own day of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, that 8th person will have to fall in to the same day as one of the others. Now, for all I know, in the group of 8 people, all of them have their birthday show up on the same day of the week. I have no way of, my claim says nothing about that case, only that there have to be at least 2 people whose birthday falls on the same day of the week. Okay, so how did that proof make you feel? Is it possible that maybe this proof is sort of unnecessary because it's referring to some pretty obvious property of weeks? That is, there are 7 days and 8 people, and if I have more people than days, two of them are going to have to share. Certainly this is a mathematical fact. Certainly this relies on some mathematical property, but it feels like it's such an elementary property that we use it all the time. It's the kind of thing you don't really need advanced mathematics education to understand. But I guess we should give it a name. And I guess I hope in the next few examples to demonstrate that once we've given this property a name and we've stated it formally, sure, there are lots of cases where it states something pretty obvious. But actually, if we know how to use it, we can use it to prove things that are pretty profound. And I find this actually is the case for a lot of combinatorics properties. A lot of things you encounter in combinatorics, a very simple, straightforward property, if you know how to twist it around and employ it in the right way, can be used to prove profound things. Okay, so we need a name for this. And basically, it relies on this intuitive idea that if you have n items and m outcomes, and the number of possible outcomes is less than the number of items, and you have to assign each item to an outcome, well, then at least 2 items have to share an outcome. There aren't enough to go around. Okay, so I don't make up the names for things like this, unfortunately, and this name was before my time, but this happens to be called the pigeonhole principle. So we're all looking forward to the rigorous mathematical reason that we call it this. Maybe it was named after somebody named Pigeonhole. I'm afraid not. So here's the pigeonhole principle. Suppose we have a group of n pigeons. That's right, the bird. And that it turns out, I'm not a biologist, but it turns out apparently that pigeons like to live in pigeonholes. Suppose we have n pigeons and m pigeonholes. And as it turns out, the number of pigeonholes available is less than the total number of pigeons. If we assume that each one of the pigeons has to be assigned to a pigeonhole, they have to choose one, then once they're done, once all of the pigeons have chosen a pigeonhole or been assigned one, then if there are fewer pigeonholes than pigeons, at least one of them has to be shared by multiple pigeons. Okay, well, I mean, if I think back, I'm flashing back through all of my career. A career has highs and lows. I don't know that I would rank the last few sentences as one of the highs, having to say the word pigeons that many times. But there it is. There is the pigeonhole principle. If you have more pigeons than pigeonholes, then 2 of the pigeons at least are going to have to share. Notice that the pigeonhole principle does not require that it only be 2. It says nothing about the actual distribution other than this one fundamental assumption that if you have more pigeons than pigeonholes, 2 of them or more are going to have to share. So for all I know, if I have 1,000 pigeons and 2 pigeonholes, well, I could break them up 500 and 500, but I could also break them up 999 and 1. So I'm not saying that every pigeonhole is shared, just that there has to be at least one that is shared among multiple pigeons. Okay, so how can we use this? If we're careful, we can actually find ways to employ the pigeonhole principle to prove things that are non-trivial, things that aren't easy to prove otherwise, and do admit a pretty easy proof if we find a way of fitting them into the framework of the pigeonhole principle. So how about this one? Consider a group of 1,000 people, and for the sake of convenience, let's assume that all 1,000 of these people have both a first and last name, and that they happen to use the English alphabet to spell their first and last name. It is no big deal. It would be very easy to adapt this problem to other alphabets and other patterns of naming, obviously, but for the sake, because, I assume people listening to this and reading these slides know the English alphabet, and we know that it contains 26 letters, let's just keep things simple and assume that we're using that. So if I have 1,000 people whose first and last names use the English alphabet, I want to prove that at least 2 of them must have the same first and last initials. And what I mean by that is, suppose you have suppose that the 2 people both have the initials AB. What I'm saying is that there are 2 people whose first initial is the same as each other, and whose last initial is the same as each other. I'm not talking about having the same first initial as your own last initial, as would be the case, for example, for me. I'm talking about having 2 different people who have the same first initial as each other and the same last initial as each other. For me, somebody that reads a lot of these word problems, I guess over the years, I have grown accustomed to to picking apart a question like this and getting a sense that maybe we want a pigeonhole principle proof here. And for me, I think the key thing is that it's just saying at least two. It's not asking me about probabilities. It's saying it wants me to prove it absolutely. So there's often the case when you're talking about large groups and a particular property that may hold among a group of people. Often that is the on-ramp into some question about probability. So, for example, we could say something like, in a group of 1,000 people, what is the probability that 3 different people have the initials AB? So that's a probability-related proof, but this clearly isn't saying that. This is saying that there must be 2 people under all circumstances. We don't know what those 2 initials are, just that at least 2 people share the same first and last initials. And that strangely general phrasing of the thing that they share, but very specific phrasing of how many people there are at least, to me always hints that maybe I want the pigeonhole principle. I have done one thing to disguise the question a little bit, which is that I just said 1,000 here. It turns out the number we need is actually considerably less than 1,000. So here's my proof. Okay, so we assume because each person's first and last name uses the English alphabet, then there are 26 choices for their first initial and 26 choices for their last initial. As I said, if we use a different alphabet or allow multiple possibilities for alphabet as far as their initials are concerned, all that changes really is this number and how I fold it into the rest of the proof. It's just, I'm using English alphabet because we know that it contains 26 letters. Okay, so that means if you have 26 possibilities for your first initial, 26 possibilities for your last initial, the total number of possible initials you could have, the number of possible combinations of first and last initial, is this number, 676, so 26 squared. And I realize now that I have 1,000 people. And if I make a list of all the possible initials they could have, so I just have them all get in line in front of their initials. So I've got, I guess I should do AA, AB, AC. We go all the way up to AZ, and then we do BA, all the way up to BZ. And we keep going until we get to ZA, all the way up to ZZ. All right, so if I take all 1,000 people and I have them line up in front of the initials that represent them, what I realize is the number of lines I'm forming is only 676, which means if I have 1,000 people line up, there has to be at least one of these lines that has 2 people or more in it. I have no idea exactly how that works. It's none of my business. All I know is that there's at least one line with at least 2 people in it. And that's by the pigeonhole principle. In this case, the pigeonholes are the set of possible initials. And the pigeons are the people. And I used the number 1,000 to disguise this a little bit, but often when you see word problems involving the pigeonhole principle, they do contain sort of suspiciously exact numbers. So maybe you'll notice that this would work even if I set the number of people to 677. And frankly, as a student, I always like this because if it says 677 and I get halfway through the proof and I get to 676, I can heave a sigh of relief thinking, okay, that clearly was what they were looking for. I must be on the right track. Well, you're getting no mercy from me. I said 1,000 people, so you have no way of knowing that that's where we were going with this. So it turns out that we need considerably fewer than 1,000 people to guarantee that 2 of them have to have the same first and last initials. Here's another one. I think that this one is actually almost profound. That is, not only is it a nice callback to something we studied earlier, but it isn't really that obvious on the surface that this is actually a pigeonhole principle exercise. And so consider an array of 114 distinct values in this range. Okay, now this is suspiciously specific. It's very strange that we're saying 114. That for me would be a bit of a tip-off that maybe we want the pigeonhole principle here. But suppose I have an array of distinct values, so duplicates are not allowed, and every element of the array is between 0 and 225. Notice that the maximum size of such an array is about 226, because obviously if I can't have duplicates and everything is from this range, at worst I can just have the entire range and nothing else. But in this case, suppose I only have 114 distinct values in this range. Prove that the array must contain a pair of values that add to 225. So I like this because it's a nice callback to our pair sum 225 problem from the first few lectures, where we discussed various algorithms that could find a pair if one existed, given an array and allowing for certain types of restrictions. Whereas here we're actually saying that under certain conditions, if the array does not contain duplicates, all values are non-negative and less than 226, and there are at least 114 of them, there must exist such a pair. So in that case, an algorithm would be pretty trivial. You just return true, I guess. So what's the proof? Well, the proof does use the pigeonhole principle, and as we've seen, the pigeonhole principle itself is pretty elementary. It's the kind of thing, as I said, that you don't need to know very much about math to know, because I think it's pretty intuitive. I think even as a kid, you could have deduced the pigeonhole principle given the appropriate setting, given a math problem that required it. That is, if you sit down with your friend and you have a platter of 5 tacos to eat, and you eat all of them, then at least one of you has to have eaten 2. That's it. That's what the pigeonhole principle is saying. Now, of course, you do need to pay for advanced mathematics classes and algorithms classes for somebody to tell you that it's called the pigeonhole principle. That's obviously something that you'd pay a premium for. But the idea behind it, before you know its name, I think is something that's very intuitive. Because of that, it is generally the case that proofs that use it, their main difficulty isn't using the pigeonhole principle, it's setting up your problem in such a way that you can use it, defining pigeonholes and defining pigeons, and finding some way of showing that you have to assign every pigeon to one of the pigeonholes that you've defined. So here's my way of doing that. So what I think about is, inside of this range, how can I get a number that sums up to 225 using only distinct values? Now actually, within the individual pairs, I don't actually have to worry about the 2 elements of a pair that add the 225 being the same, because 225 divided by 2, which is 112.5, is obviously not an integer. So if I have integers, I know that anything that adds a 225 have to be 2 distinct values. Okay, so let's think of the possible pairs that add the 225. There is 0 and 225, 1 and 224, all the way up to 111 and 114, and 112 and 113. And now what I do is I make up a bucket for each of these possible pairs. And I go through my array, and I guess I should point out that the number of possible pairs here is 113. So the first index of the pair counts from 0 up to 112. That's 113 possible pairs. There are 114 elements in A. Okay, here's where I heave a sigh of relief. I found 113 things, and it sounds like maybe those are going to be my pigeonholes. And now I notice that I've got 114 elements in A. That lines up a bit too conveniently to be a coincidence. So what I do is I walk through my array A. Let's just make up an array A here. So suppose that A is... let's do 0, 111, 112, and then 1, and then maybe 225, and then some more stuff. What I do is I walk through my array A, and I just take each element and I throw it into whichever bucket contains that element. So notice how each of the values in my range only is in one of these buckets that I've defined. So I go through my array and I throw each thing in the bucket, and I know that because array does not contain duplicates, once 0 is in this bucket, I will never see a 0 again in the array. So if anything else gets thrown into the bucket, it must be the number 225. Okay, so I throw 111 in this bucket, I throw 112 in this bucket, I throw 1 here, and then I get to the 225, and I put it over here. Okay, so in this case, I was lucky, and I found a pair very quickly. The argument I'm going to make, though, is the number of buckets is 113. I'm going to distribute 114 elements into my various buckets. And that means there are not enough buckets to go around. There's no way I can give each of my 114 elements its own bucket to fall into, its own pair to itself. So therefore, there have to be 2 elements of A, let's say AI and AJ, which fall into the same one of my buckets. I don't know which one it's going to be, and I don't care. I just know that there will be 2 that fall into the same one. And once I have both things in that bucket, well, then that means there are 2 things in A that add to 225. And so by the pigeonhole principle, in this case, an array A of 114 distinct values in this range must contain a pair of values that adds to 225. I hope that that's enough to show that the pigeonhole principle, when properly employed, is very powerful. And maybe the reason for that is that maybe it wasn't doing all the work here. Maybe the work was being done by the rest of the proof. But whatever, I needed some way of sealing the deal. I needed some way of establishing at the end, once I have this number of buckets and this number of elements thrown into it, that there is some mathematical principle governing that requires such a pair to exist. Okay, so why are we talking about this? Well, I mentioned at the beginning that the study of hash tables and hashing actually involves a lot of skills that we haven't really used that much in this course. We've had quite a focus on things like discrete math in this course. We've used continuous math occasionally. So, for example, when we talked about asymptotic notation, we did use limits. And I assume everybody coming into this course has a background in calculus and discrete math and probability and some statistics, although we don't generally need very many statistics in this course. It's good to know about that. That's good background to have to talk about any scientific topic. The study of hashing does involve some discussion of probability. And although this lecture doesn't really require that very much, I am going to gratuitously bring up probability later, because I have an ulterior motive of setting up an exercise that I want to give. So, I mean, I'll admit to that right now. And one of the skills we have to have when talking about hashing, beyond understanding probabilities and having some basic understanding about randomness, is also some understanding of combinatorics. And the pigeonhole principle plays into that. We're going to see that I have to invoke the pigeonhole principle about halfway through this lecture. So here we are back at the dictionary data type. And remember that I've mentioned this repeatedly over the past few lectures. The dictionary has these three operations, and some might be more important than others. And although this is not the first time I've made this point, I think it really becomes evident in this lecture under what circumstances I might be willing to be pretty flexible about running times, and that we should think about that. That in a data structure, sure, we already talked about that if we use an unsorted array for our dictionary, we get different running times than if we use a sorted array, and so on. I guess I have that. Nope, I don't have that. I have that somewhere else in this lecture, the table of all the different running times. But the trade-off that I'm willing to accept actually could be a great deal more tilted than that. So what I want to observe, I want to do a recap here. I want to observe that if we go back to when we were just talking about single algorithms, so I would say something like design a comparison sorting algorithm, or design an algorithm for the selection problem, or give me an algorithm to compute a convex hull. If I'm just talking about one algorithm and all I care about is worst case running time, really what I'm doing with my design process is optimizing for a single parameter. That is, if all I care about is having a low worst case running time, then all I have to worry about when I am designing algorithms is how to bring that number down. If I have an n squared algorithm, all I think about is, can I make this n log n? Can I make this n? Can I make this constant? Whereas if I'm implementing a data structure, I now am optimizing with respect to more than one parameter. And so there's more trade-offs that I have to make, and there are, I guess, more ways that I might be expected to compromise. And we talked about this with the discussion of binary search trees, that sure, I might be willing to put up with, in some cases, a big theta of n insert operation, if in exchange I got a big theta of log n find operation. And that might be a reasonable compromise to make because I expect under most circumstances, the find operation is more important. I'm going to use it more often. Now, actually, it turned out we got to have our cake and eat it too. I was able to get a log n insert and a log n find and a log n remove. But even then, at the end of the last lecture, I pointed out that it's nice that in a red-black tree, we get to use the ordinary binary search tree find operation. Because even though these are all asymptotically the same, there are still going to be differences in their running time. And we know that insert and remove are definitely a little bit slower operations in a red-black tree because of all the extra constant time work that we have to do. Whereas the find operation is pretty clean and streamlined. And so one compromise that I think is very reasonable to make is I am happy to allow, to have a running time of 999 times log n for my insert operation and remove operation if in exchange I get a running time of maybe 1/2 times log n for my find operation, or 1 times log n for my find operation. So even if the asymptotic running times are equal, we should be conscious of which operations are more important than others as far as running time is concerned. What I want to talk about in this lecture, among other things, so besides discussing hash tables, is I finally wanted to talk about cases where maybe the worst case running time ceases to be my highest priority. Where if you offer me a good enough deal, if you make me an offer I can't refuse, I might be willing to put up with worst case running times that are actually worse than ones we've already seen. So although we've seen a case where I can get insert, find, and remove at log n time, I'm going to show off in this lecture a situation where I'm willing to accept worst case linear running time for all three operations in exchange for a guarantee that in the vast majority of cases, I will not see that worst case running time. I'm not being guaranteed that I will never see it, but we can actually establish, using, for example, knowledge of probabilities and randomness, we can establish that the worst case is so unlikely that I'm willing to accept that worst case linear running time in exchange for getting an expected running time. So on an average input, I get a running time that is constant. Now, I don't know if I would make that trade if I was only getting a log n running time. If you give me an expected log n running time and a worst case linear running time, I might say, hey, I'll just use a red-black tree, which guarantees me log n. But constant running time, that's a pretty good deal. That might be something I can't pass up. As long as you can guarantee me that this is extremely unlikely, I might be willing to take that deal. And so that's what we're going to see in this lecture. And that's one of the reasons hash tables are so important, is that hash tables don't give us a good worst case running time guarantee, but they do give us guarantees about the likelihood of a worst case input. And we can assert, and it turns out though that some of these assertions are things we can't actually prove in this course, and we're not going to. But if you take a higher level course in randomized algorithms or algorithm analysis, you'll be able to see this. We can actually assert that the probability of a hash table actually seeing a worst case input can be extremely low. And therefore, because we can write proofs to that effect, if we're getting constant time performance on an expected input, and that expectation is very likely to be achieved, then maybe I'll take that deal. Now, I've gotten way ahead of myself. Before I talk about hash tables, let's talk about something else. So describe a dictionary implementation with fast searching, insertion, and removal. I won't say how fast yet, but in this case, I'm restricting all of the keys to be integers in the range 0 through 10 inclusive, and no duplicates are allowed. Okay, so this constraint isn't too controversial. We've actually been working with this constraint for the past few lectures. This one, though, is a pretty big deal. So this lecture is a departure from the model we've been using for the past few lectures, where we were assuming a comparison framework. So in the past few lectures, we were assuming that all we knew about the keys was what we could learn from performing comparisons like this. In this case, I'm saying assume the keys are integers. And just like how, when we began talking about non-comparison-based sorting, we were allowed to make some assumptions that made things a lot faster, we should be able to do the same thing with dictionaries. If I'm allowed to assume all of my keys are integers, especially if they're integers in a tiny range, hopefully I can speed things up. I shouldn't need a red-black tree to make this fast. Now, for this particular problem, where I'm storing a collection of things in a very confined range and all of my keys are integers, I would use a very simple 0-1 array, basically an array of truth values. And what I would do is I would use indices as a quick way of looking up whether a particular key is in the collection or not. So the keys here, in a sense, are the indices, and the value inside the array is a truth value, yes or no, is this key in the collection? So the collection I'm storing here contains the keys 1, 3, 8, 9, and 10. And if I want to do a lookup, if I say search for the value 3, what that means is go look at index 3 and just tell me what it contains. If it contains 1, well then the key 3 is in my dictionary. If it contains 0, then it isn't. And hopefully you can see that that means that looking something up is constant time. And it's not just constant time, it's a very fast constant time. It requires very little actual work. Okay, so that's what the slide's saying, what I just said. Now, I should observe, and this is the only time I'm going to bring this up during this lecture, as I've been doing in the past few lectures, I'm pretty much ignoring the idea that the dictionary actually stores key-value pairs. I just worry about the keys, because in the dictionary, the only thing I can use to organize my collection is the key. But there are these values, these arbitrary pieces of data that ride along with every key. What I want to observe here is that there's no reason that this representation prevents me from doing that. So suppose I want to store values with each of my keys. What I would do in that case is, suppose I want to store 1 associated with something called V1. So V1 would be the value corresponding to key 1, V3 might be the value corresponding to key 3, and so on. What I would do is have the elements of my array just be the values, or be a pointer to the values. So I keep the values somewhere else and have my array point to them, or something. And then in the elements of my array that do not contain a value, where the key is not present, I would set them to maybe a null pointer or something. So that means if I want to do a lookup, so I want to ask, is key 3 in the collection? And if so, give me its value. I go to index 3 of my array and I ask, is this a null pointer? If the answer is no, well then it's in the collection, and whatever's in the array is a pointer to my value if I need it. So hopefully it's clear that I can still store values that ride along with my keys, even if I use this unconventional table representation for my collection. And having said that, I'm never going to refer to this again. So for the rest of this lecture, as I talk about tables, keep in mind that it is very easy to keep a value, a pointer to some arbitrary data value associated with each key, or keep a separate array full of values or whatever. That's easily possible. It's well within reach of all the techniques we're using, and because we don't care that much about the values as far as organizing things, I'm never going to refer to them after this. Okay, so the solution we just saw here, this table, only really applies if the keys are integers, because what I'm leveraging here is fast array indexing. And obviously I can't index an array by anything other than an integer. Additionally, I need the range of possible keys to be small. And we'll see a concrete example of why that is in a minute, but I think that's sort of intuitive. That is, if my key could be the number 1 billion, well then I have to have an index in my array for the number 1 billion. The problem that I defined is one where the range was deliberately really small, and so it's very easy to define an array of size 11, as I have here. I should add that I consider this particular structure not even to be something we need to take an algorithms course to learn about. This is a basic programming technique in my books. And in the types of code that I find myself writing all the time, that is, I often have to write code in a language like C or C++ or Java, where I need to define my own data structures, although I will admit mostly it's C and C++, not really Java that much. When I have to do that, I actually often find myself, for some reason, the types of problems that I work on, I often find myself having to store, for example, sets. And the sets are subsets of some relatively small range of integers. So I might have a set which is a subset of 1, 2, up to 10. Actually, let's have that include 0 so that we can actually make it map onto this case exactly. If I'm representing a subset of some relatively limited collection of integers, then this is a perfect representation because a set doesn't require any inherent ordering, so I don't need to use a sequence to represent it, but usually you want to be able to perform fast lookups using a set. I want to be able to ask questions like, is this element X in my set or not? And this table-based data structure gives me everything that I need in constant time. And if I want to list all the elements in the set, then I have to iterate over and just print out all of the indices where the element is set to 1. But that's also not very difficult. And if I only care about iterating over something, then I might use a sequence type. So I consider this is only coming up during this lecture because it happens to be a good prelude to our main topic. But I consider this technique of using a basic array as sort of a fundamental programming technique. It's the kind of thing I would bring up in first-year programming before we even got to talking about things like linked lists or anything more advanced than that. All right, here's a variation on that. Describe a dictionary implementation which can store n keys in the range 0 through 2 times n. And this is sort of important because what I just had was a dictionary where the keys have to be between 0 and 10, which means the maximum size of my collection is bounded. I mean, it's going to be at most 11. I can't have any more than 11 things in the range 0 through 10 if duplicates aren't allowed. So can we generalize this amazing constant time table lookup trick to cases where my collection could have an arbitrary size? So that's what this is asking. I have n keys, they're distinct, there are no duplicates, and they're in the range 0 through 2 times n. And I want constant time, and I mean worst case constant time, find, insert, and remove operations. Well, the answer is I just do the same thing. I just make an array of size 2n, or actually the array's actual size here is 2n plus 1 because I start at 0 and go all the way up to 2n. Once I have my array, the lookup time is constant. So if I want to add an element, so if I say add the key 2 to my collection, I just go to index 2 and put a 1 there. If I say remove the key 2, I just go to index 2 and put a 0 there. If I say look up whether key 2 is in my collection, just go to index 2 and inspect the element. All of that's constant. Now, I actually have to create the array. So the dictionary operations don't include anything for like the constructor, for initializing it. And that's because the dictionary has 3 main operations, insert, find, and remove. It is assumed that initialization is necessary, but we don't really care how that works. It is worth noting that this particular structure does have linear time initialization complexity, whereas let's say a red-black tree might not. A binary search tree, when you initialize it to be empty, that initialization is constant time. We just, create a root pointer and set it to be null. Whereas for this table representation, we need linear time to create a table of linear size. So obviously 2 times n is a linear quantity. That's big theta of n. And that means I need linear space to store my table. And creating something that requires linear space requires linear time. But all that's in initialization. Once I've created the table, I can use it and perform all of my key dictionary operations in constant time. And so, as I said a minute ago, I really love this representation. Maybe it's just me, but I really like this, and I think because I often write code where I'm working in a relatively low-level language like C or C++, although C++ does have a standard library that I can use, there are lots of reasons why it might not always be the best idea. So, for example, in work that I've done writing algorithms for data compression, where the algorithm is very performance intensive, we want it to be extremely fast, and it's doing a lot of very complicated work, often creating creating stuff from the standard library takes too long. In other work I've done that's been involved with like large-scale computational searches, again, if we're solving a problem that might require exponential time to solve, we want to save every clock cycle we can. And in those cases, basic arrays used to store sets and collections can be a lifesaver. So I really love this technique, and in general I recommend if you find yourself requiring a dictionary where the keys are integers and the range is relatively constrained, so probably linear in n, maybe n squared or something in certain cases, a basic table is often your best bet. Although creating the table takes a while, if you have enough memory for it, once you have the table, all of the key operations are extremely fast. Not only are they constant time, but they're a tiny constant. All you're doing is a single array access operation, indexing into an array. All right, but the problem is that we don't often have that luxury. Often the keys in our dictionary aren't in some restricted range. So how about this? Describe a dictionary implementation that can store n keys in this range. And it does feel like we should explore this possibility because we often find ourselves working with keys where the set of possible keys is much larger than the size of the key or the number of things in my collection. So n here is the number of items in my collection. And if I'm storing a collection of different integers or something, it is reasonable that the integers themselves could have a range that is exponential relative to the size of my collection. So think about this. Suppose I want to store 32 integers and they're all 32-bit values. Well, then they're all going to be in this range here. So approximately 4 billion possibilities. Well, I could use a table as before, but now I have to make a table whose size is 2 to the n, well, 2 to the n all plus 1 because I'm starting at 0 as before, which means even though I would actually get constant time lookup, insert, and remove, because by our random access model, even if our array is ridiculously large, accessing any particular index of it does require constant time, I would need to create a table of size 2 to the n. Now, at minimum, even if you have a computer with a ridiculous amount of memory, at minimum, that means I need to spend 2 to the n time creating an array. And that means for even relatively modest values of n, like, I don't know, n equals 50 or something, you're going to be creating that array for the rest of your life at this point. I mean, that's a huge amount, a massive array, 2 to the 50, of size 2 to the 50. That's one problem. Another problem, a far more concrete one, is you don't have this much memory. I mean, I don't know when you're watching this, but you don't have this much memory. And if you do, I mean, I don't know how that's possible. If in some museum tour you are taking in the future, 10,000 years from 2025, you'll have to look up what 2025 means because I'm sure in the future you don't necessarily use the same system of dates as we do. Maybe you're not on Earth and you don't use solar years. I don't know. But in the future, if you're watching this and you somehow have computers with this amount of memory, then first off, why are you watching this? Aren't there better algorithms courses by now? And also, even so, you probably don't have this much memory. So the problem with exponentials, of course, is that even if you can manage to run an exponential time algorithm or allocate exponential space, I don't have to adjust n by very much to make the problem intractable again. So we talked a bit about exponential time algorithms back in, what was that, like lecture 12 or so? And I mentioned that, yeah, there are some algorithms, there are some problems that we don't seem to be able to solve faster than exponential time. But if we're careful, we might be able to solve them on an instance where, I don't know, n equals 100 or something. But the problem is, if your algorithm is nominally, has running time, worst case running time 2 to the 100, and just by the way, there's no way you're actually running the algorithm for that number of steps. If you actually are able to solve it on n equals 100, either you've made it a little bit faster exponentially, so it's like 1.5 to the 100, or more likely, you're not looking at a worst case input. Even if you could solve a problem that required this amount of time, if I increment n by 1, so if I say n equals 101, well, now you're talking about 2 to the 101. That's twice as long. So if I increment n, if I double n, then now you're talking about something that requires 2 to the 100 times as long. And so when you're working with exponential functions, even if you can achieve the exponential complexity for a certain value of n, I don't have to change n by much to make it impossible for you again. So although you do not have a computer with 2 to the 100 units of memory, yes, even you in the future watching this thousands of years from now, even you don't, although you don't have a computer with 2 to the 100 units of memory, even if you did, you don't have a computer with 2 to the 200 units of memory, so this isn't really a sustainable strategy. As far as today's computers are concerned, so that is to say, if we're talking about trying to create a table of size 2 to the n today, well, I might be able to solve this. I might be able to create a table of size 2 to the 36 or something, maybe, on a computer with a ton of memory. And the problem with space consumption is that, although theoretically at least, if I wanted to run an algorithm whose running time was 2 to the 100, I could just sit and wait if I wanted to. Now, don't do that. It's going to take the rest of your life. But if I wanted to run an algorithm whose running time was, I don't know, 2 to the 40, yeah, I actually could just wait for that to finish. That would take a long time, but I could wait for it. Running time, strangely, is actually the most plentiful resource that we have on a computer. Because it's true that some algorithms take too long, but if I want them to finish, I could always wait. I could just sit here for as long as it takes. Other resources that I might have in a computer, like bandwidth or disk space or memory, are finite and they are bounded, and I can't increase them unless I go buy more. So if I don't have 2 to the 40 units of memory, I cannot create an array of size 2 to the 40. It cannot happen. I might be able to wait while an operation takes 2 to the 40 units of time, but unless I go buy more memory for my computer, I cannot create an array that's too big. Okay, that was a whole bunch of different stuff that I just said. I hope that together, taken together, that was enough to justify that this is not a practical way of doing things. Even though if I had a table of size 2 to the n, I could do constant time lookups, insertions, and removals, it's unlikely I'll be able to use that for most practical cases. So unless I'm working with a situation where n is incredibly small, this particular problem cannot be solved with a basic table. Now, I said earlier, though, it's often the case that you can solve problems with a basic table because you don't have such a bizarre distinction between the number of keys in the collection and the range of those keys. That is, if you were storing something between 0 and 2 to the 32, you could probably make a table of size 2 to the 32 in your computer right now. And even if you're storing, I don't know, like 2 to the 16 or 2 to the 30 things in that table, as long as they're distinct, this is a viable option. The issue is, in general, we can foresee lots of cases where the keys that we're storing in our dictionary come from a collection with a size far larger than the size of our collection that we're storing. That is, I might store n keys that are drawn from a set of possible keys that could be exponential in size. Integers don't really give us the perspective we need on that. Suppose that I wanted to store n strings. Just strings of any length. How many of those are there? Well, I think you can agree they're an infinite number, because strings can have any arbitrary length. Theoretically, at least, the number of possible strings is infinite, clearly. But even if I say n strings of length, less than or equal to 10, how about that? Okay, well, there's only a finite number of strings less than or equal to 10. Okay, wait, what's a string? Let's assume that a string is a sequence of bytes. Okay, so what I'm actually talking about is I'm talking about storing 10-byte sequences. That's a lot. There are a lot of possible strings of length less than or equal to 10 if each character in the string is 1 byte in size. And so, of course, I can't make a table with size equal to the number of possible strings. As an exercise, go ahead and try and work out how many of them there are. It won't take very long, but it's a lot, and we can't do that. Okay, so this isn't going to work. However, what I basically want to observe about this is that the idea of using table lookups is a good one. If we're lucky enough to be able to use table lookups, we get a huge amount of a benefit from it. So we get the ability to do a simple array indexing operation, which is basically, not only is that constant time, it's almost instant. It's like 1 or 2 operations, a small amount of arithmetic and then going to memory. And maintenance of the table is relatively simple. The problem is we can only use a table in the event where our keys can easily be mapped to indices of a relatively small array. Even if we could create a table of size 2 to the n would be, the value of n is so small that most of the table would be wasted. The vast majority of the space that I've allocated would be empty space. And that doesn't make very much sense, even if I have that memory available. And remember that I'm actually a big proponent of wasting space. Back when we talked about implementing heaps using an array, I pointed out that, hey, if you want a 1-based indexing array, just make one that starts at 0 and pretend that index isn't there. I am all in favor of wasting space if it results in more efficient algorithms or faster algorithms. On the other hand, I don't want to waste any more than, I don't know, maybe big theta of n space. I don't mind creating an array where half of the slots are empty. I don't even mind creating an array where 1% of the slots are filled, like maybe 99% of the space is empty. But I don't want an exponential number of positions to be empty. That seems a bit excessive even to me. So here's an idea. I like table lookups, and I like this idea of being able to just map a key in my collection to some index of the array. So why not come up with a clever indexing scheme that wastes less space? So if I only have n elements, I shouldn't need a table of size 2 to the n to store them. Maybe having some empty space is beneficial. I'm not sure whether that's the case or not, although, spoiler, it turns out that it is. Maybe having some empty space is beneficial, so I can admit the possibility of maybe making a table of size 10n, or maybe 100 times n. So 99% of that space is empty if my collection has n elements in it. And then I use some trick to map elements of some, massive set of possibilities, so 2 to the n possibilities or 2 to the 2 to the n possibilities. I use some indexing scheme that allows me to cram all of those elements into a set of indices that's much smaller. So for example, suppose I have this collection here, and these are all 2-digit numbers. So of course, if I wanted to, I could store them all in a table of size 100 or 101, if I just use them directly as indices. But I think that might be a bit of a waste. I only have 5 things. I don't want to make a table of size 100 or 101 to store just those 5 things. So how about this? I'll use a modified indexing scheme where I just take the last digit of the number. So for a 1-digit number, that would just be the only digit. I take the last digit and I use that as the index. And then I cram everything into a table of size 10. Now to do this, it's no longer viable for me to just put zeros and ones, because I now have to keep track of, since I have fewer indices than I have possible keys, I have to have some way of knowing exactly which key is occupying each index. So what I'll do here is I'll just store the key in the index. So when I insert the value 10, its index is 0, that's its last digit, and so I put it in index 0 of the array. And then I just put 10 there to make sure you know when you go looking that that's what's in that index. Because if later I do a search for the element 10, I'll go looking in index 0 and I'll find there it is. Similarly, I put 17 in index 7, I put 29 in index 9, I put 92 in index 2. So I have a very basic indexing scheme here. It corresponds to this function. So I call the function g on my key, and it spits out an index in the range of the size of my table. And then I could do searches using the same idea. So because I'm using a modified indexing scheme, any access into my table has to use this new function I've defined to govern the indexing. So let's say we go searching for the key 15. Okay, so the first thing I do is I plug 15 into G, and that's going to return. You can see that K mod 10 would just be the least significant digit of the value in base 10. So G of 15 would be 5. Okay, so I go looking at index 5, and I ask the question, is 15 in there? And the answer is obviously no, which is my way of knowing that 15 was not found in the dictionary and that my search was unsuccessful. And we can see that that was constant time. So in this case, and an assumption I'm going to make throughout this lecture is that these functions I use for indexing can be evaluated in constant time relative to n, relative to the size of my collection. They may take a variable amount of time related to the size of the key, which I'm not going to worry about for this lecture, but the amount of time they take is constant with respect to n, with respect to the number of keys in my table. So I go look at index 5, it's empty, and I can conclude, therefore, that key 15 is not present. Because if I had inserted key 15, that's where it would be. So I went to look at the only place it could be, and I didn't find it there, so it must not be there at all. Let's go search for something that is there, 92. Okay, so the value of G on 92 is 2, so I go look at index 2, and it does contain 92, so I guess I found it. It's in there. And that find operation was constant time. And hopefully you can agree that an insertion is also constant time. So if I go to insert the value, I don't know, like 34, then it would go into index 4, and I just put it there. Evaluating the function G is constant, going into the array is constant, adding the element is constant, so it's all constant time. All right, let's search for 27. Okay, so I go look for the key 27, and I take its last digit, so I evaluate G, and that gets me 7. And then I go to index 7, and I look in there, and I'm like, well, there is something in index 7, but it's not 27. And the only place 27 could be in this array is there, so since it's not there, since something else is there instead, 27 is not present. Okay, and that was all constant time as well. Okay, so we didn't find 27. Let's add it. I mean, that's a valid operation, right? I should be allowed to add any key I want to this dictionary. If the prompt was design a dictionary that works with all 2-digit numbers, everything in the range 0 through 99, well, then I should be allowed to insert 27, right? Okay, so we evaluate G, and we get 7. We go to index 7, but yeah, it's full. So what do we do? I guess it's impossible to perform the insertion. The slides are trying to be magnanimous, and they say, unless you discard an existing key. But I'm not allowed to do that, of course. The dictionary ADT doesn't allow me to, at my discretion, just delete keys from the collection. Unless a remove operation is called from outside, I'm not allowed to delete 17. This is a problem because 27 needs to go here. My indexing scheme tells me this is where 27 goes. But I shouldn't be too surprised that I ended up in this situation because I have a table that's much smaller than my total space of keys. There are not enough table indices for every key to have its own index. And so in the event that two keys fight for the same index, I'm going to have this problem. And so I'm going to argue that I just have to fail. The insertion cannot be performed. And because it wasn't possible to perform a valid insertion, the data structure is now a failure. So recall, one of my general pieces of advice throughout this course has been, we should first write an algorithm that is slow before we work on a fast one. And this is not advice relevant to the current situation directly, but there are those people out there that when you tell them to write an algorithm to solve a problem, they get obsessed with writing a fast one. And they begin working on a fast one that ends up being broken. It doesn't work in all possible cases. And remember that a fast broken algorithm isn't an algorithm at all. It's much better to have a slow working solution than a fast and broken one. And here, I had what I thought was a clever trick. But it turns out it's a failure. This is not a dictionary, because if I can't perform a valid dictionary operation, then I don't have a dictionary after all. And so the data structure simply fails. And the reason is because it is perfectly reasonable for the dictionary user to want to insert multiple keys with the same last digit. How should they have known that that was a sensitive aspect for this implementation? Now remember that it is valid when you provide a dictionary implementation to somebody to state certain restrictions. You can say things like, I'm assuming that there are no duplicates. So you're not allowed to insert duplicates. If you try and do that, that's your problem. You can say all elements are in the range 0 through 99. You are even allowed to do that because they can choose not to adopt your dictionary if they want to have different keys. But in a dictionary with these constraints, arbitrarily saying, sorry, for some reason 17 and 27 don't get along with each other, that's not a good reason. The dictionary has failed in that case. I suppose you could add a constraint that says you can't have two keys with the same last digit, but it seems like that constraint is so esoteric that nobody would accept that what you've created is actually a dictionary implementation. In general, when you store keys in a dictionary, it's very common for the keys that you store to have some kind of internal patterns to them. Because think of why you use dictionaries. We might use a dictionary to store a database of, I don't know, like employee records or people's names or phone numbers or email addresses, and those have lots of patterns. So every email address contains this symbol, for example. There are lots of internal patterns that can show up in the keys in a dictionary, and it's sort of the dictionary's problem to resolve that. The dictionary shouldn't be allowed to reject certain keys because there are patterns that show up, especially bizarre arbitrary patterns like having the same last digit. So although this function g was useful for compressing the set of possible indices into a range, the range being 0 through 9, the indices of my table, it doesn't spread the keys out evenly. Now, that's not the only problem we have here, because you can think about this. If you had a function that did a better job of spreading everything out with no obvious patterns in what it did, you still would eventually have two keys bump into each other like this. But I'm arguing for the time being we should focus on that problem. That is, because G only takes into account a certain amount of information about the key, that is, only its last digit, there are these obvious patterns to keys that we could use to produce this problem. So if you know that G uses only the last digit of a key, you could easily make a list of different keys that G is going to have a problem with. So for example, I could do 14, 24, 34, 44. It's easy for me to exploit the logic of G, the fact that it only takes into account the last digit, to construct a sequence that are going to give this implementation indigestion. So maybe what we should do, by way of trying to slowly remedy this problem, is begin by designing an indexing scheme that doesn't just incorporate one aspect of our key. It tries to incorporate as much of our key's data as possible. And I guess my goal here, so let's consider 11 and 21. They both have the same last digit. My goal is that if I incorporate both digits of the number, then ideally I have an indexing scheme such that if one digit is different, then the index will be different. So even if there's only a minor difference in the characteristics of the data in the key, the index I get assigned is going to be different. So I don't have to worry about an obvious pattern like this resulting in both of the keys getting the same index. So how about this one here? So it looks a bit complicated. The slides describe what it actually does, but I can tell you what it does in an intuitive sense. What H is doing here is it is adding together the two digits of the key. So let's take a look at the key 47. So h of 47 would be 47 plus, okay, well, what's this? The floor of 47 over 10. This is 47 under integer division by 10, so 4. So 47 plus 4, that would be 51, and then 51 mod 10 is 1. And if I add the two digits of 47 together, 4 plus 7 equals 11, and then take that mod 10, so 11 mod 10 is 1. So actually this function essentially just adds together both of the digits, which is sort of a good idea because now it means if you have two different keys with the same last digit but different first digits, h of k is going to give them different indices. So one big rule for hash tables, which we're building up to here, is that when we design a function to produce our indices, it should try and take into account as much information about the key as possible. Anything that defines the key, any aspect of the key that can be used to define it, should be incorporated somehow into the indexing scheme. And actually, while we're on the subject, we've got this new function h. And I guess we're going to be talking a lot about functions that map keys to indices, and I've already begun to state certain philosophical goals of those functions, things like they should incorporate as much of the data as possible. I guess we should give them a name. We're going to call these things hash functions. Now, I don't really know that there is really a like definitive version of the story of why they're called that. Like there are lots of weird sort of folklore about why it's called a hash function. I guess the one that I think makes some sense to me, and it's the kind of name that would have caught on back in the day when these things were being invented, is that the point of a hash function is to take some key, and it could be a key of any type, not just an integer. It could be a string, it could be some arbitrary data record, and it takes that key and it sort of takes all the data inside it and mashes it all up together and then spits out a single integer index. And so you can think about a hash that one would make when you're cooking something, or hash browns or something. You're just mashing everything together and making one single thing out of it, and that would be an integer index. We call that thing a hash function. And in general, hash functions are more effective, at least in the case that we're thinking about them, if they take into account as much different information about the key as they can, as many aspects of the key's identity as possible. And as I said a minute ago, because it takes more information into account, it seems less likely. We're going to see that word a lot this lecture because we're actually talking about things that border on the study of probability, less likely that two distinct keys will be assigned to the same index. Although it turns out that's still possible, and that possibility is something we can't avoid in general. Now, it turns out that although h is a hash function, and actually g technically was a hash function as well, we're going to see in a minute that h is not the most effective hash function. There probably are better hash functions that we could work with. Let's insert these keys into my table using this new function h to compute the index. Notice that all four of my keys have the same last digit. So under my previous scheme, where I was using the last digit only, I would run into trouble very quickly with this sequence. But with h, we get 1 goes into index 1. 11, because 1 plus 1 is 2, goes to index 2. 21 goes to index 3. 31 goes to index 4. So h was able to spread them out nicely. Now, it doesn't spread them out perfectly across all indices of the table. They're all in a row here, but it doesn't try and put two of them in the same index. So we have managed to improve at least somewhat on our function g. So although it's true, as we just saw, that h will map keys with the same last digit to different indices, there are still going to be collections of keys that can map to the same index. And this is actually a problem that we can't avoid in general. And the reason is pretty simple. There are only so many indices. There are far more keys possible than there are indices of my table. This is beginning to ring a bell, actually. So an exercise, I almost did this exercise, but I remembered it was coming, is to find a collection of 10 keys. Find me 10 two-digit numbers that this particular function all sends to index 5. And it's useful to try this because if you go through a few of these exercises, you learn that there are certain patterns you can exploit. It actually is relatively easy to find sequences of keys that have this property. Once you've tried it a few times, it becomes pretty easy to see the patterns and how you generate them. Okay, so what have we just done? This idea of using a function and a simple array as a way of implementing a dictionary is a data structure called a hash table. And it's called a hash table because it's just a hash function in a table, basically. It's all in the name. It's a combination of an array, which I'm just going to keep calling a table for our purposes, and a hash function. And it stores some collection of keys. And values. There's also values in there, but we don't care so much about those. We know they can always be stored somewhere. We're going to use this convention of using the letter M to represent represent the size of the table. So in the previous example, m was equal to 10, because we have indices 0 through 9. N will be the number of keys in the table, the size of my collection, and h will always be our hash function. So for the rest of this lecture and the next lecture, if I say m, I mean the table size. If I say n, I mean the number of keys. And if I say h, I mean the hash function. Because, as I've mentioned, it is important for us to consider the keys that could ever be inserted. So in this example, these are the keys I have in my collection, and n equals 4. But the set of possible keys are the two-digit numbers, 0 through 99. And I do need to think about that. It's often important to reason about the set of possible keys to characterize how well the hash table will behave on random inputs, on average inputs. If I choose 4 random two-digit numbers, what will happen with this hash table? So I need some way of talking about that. And so we're going to call the set of all possible keys, so keys that somebody might ever insert, will be called the universe. And we'll denote it by capital U. And in every other source that you read about hash tables, typically it's also called the universe and denoted by some other capital U, whether it's a plain sans serif U or some weird calligraphy version, I don't know, but it's usually called U. And as I guess we've sort of been assuming all along, we're generally going to assume that the set of keys that ever actually get inserted. So if I make a hash table where the keys come from some universe U and I insert a bunch of keys, maybe I insert 10 keys, maybe I insert 1,000,000 keys, but the keys I insert will generally, we're going to assume, be a very, very small fraction of the set of possible keys. So if I, for example, store a dictionary where the keys are strings, well, I might insert 1,000,000,000 strings, but the number of possible strings is infinite. It's much larger than 1,000,000,000, certainly, even if it's limited to some specific size. So we're going to act on the general assumption that the size of our universe is much larger than the number of keys we ever actually put into our table. A couple of other restrictions for the sake of our convenience. I'm going to require for this lecture, for our purposes, when we discuss hash functions, I'm going to assume that the output of a hash function is always a valid index for our table. So if our table has size m, I will assume that to be considered a hash function, h must always produce an index between 0 and m minus 1. So if you give me a function that produces some arbitrary large number greater than m, it isn't a hash function. It's up to you to try and make that, to adjust h to emit indices between 0 and m minus 1. Now, this isn't really a limitation. It's mostly a notational convenience, because if you have some hash function you want to use that generates numbers larger than m, so let's say you have a function g that you want to use as a hash function for your table of size m, you could always define g mod m as your hash function. So it's easy to adapt a function to generate indices between 0 and m minus 1. Just take everything mod m. What we're going to see, and what may have already been sort of clear, is that the overall effectiveness of a hash table is pretty much up to the hash function. I mean, as we saw, a hash table is just a table and a hash function. There are some bits of machinery we have to define to address certain weird cases that can arise, and those are important, but ultimately the performance, how fast your operations are, really does come down to the effectiveness of the hash function. In general, we want a hash function that can be expected to spread keys out pretty evenly among the indices of the table. So no matter what sequence of keys I insert, I want the hash function to spread them out evenly, and we'll see why that's beneficial, well, mostly in the next lecture, why the even distribution is so important. But certainly I want, if I have two different keys, I want it to be very unlikely as possible, that they end up getting stuck in the same index, because certainly that's already been a problem for us. In the case where we have a good hash function, hash tables can provide amazing performance. What we're going to see pretty quickly, though, is that a good hash function is sort of an ideal. It's not something we can easily implement. We can create hash functions that are good enough, but it's very hard to prove a hash function actually meets the criteria that we are going to set for a good hash function. Okay, so one other thing. I mentioned a few minutes ago that initial problem where both 17 and 27 ended up with the same index could be solved by changing our hash function so it distributes things a bit more evenly with no obvious patterns, so that two things with the same last digit don't end up in the same index. But I also pointed out that actually the overall problem is not something we can avoid, and it's a problem called a collision. If two different keys, K1 and K2, have the same hash value, if they both get assigned to the same index of the table, then we have a problem. And we call that thing a collision. K1 and K2 collide under our hash function. The problem is that that's inevitable. So we can try to avoid collisions where there are obvious patterns, like same last digit, but in general, if my table size is smaller than the size of my universe, if the number of possible keys is larger than the size of my table, then collisions are guaranteed, because the hash function has to cram a large number of possible keys into a small space. And we've got m pigeonholes and the size of u pigeons. And the hash function has to map all of the pigeons into one of the pigeonholes. I may not use all of the pigeons at any given time. Any given hash table may not contain every possible key, but the hash function must accommodate every possible key. And so the existence of collisions is guaranteed by the pigeonhole principle. If you're working in a setting where your table size is larger than the size of your universe, then you don't need a hash table in the way that we're describing it. You could go back and use the very simple table representation we described at the beginning. And because the set of keys you're going to store in your hash table, so if you use a hash table to implement a dictionary and somebody creates a hash table and then calls insert on it, you don't know in advance which keys they're going to insert. So since the exact set of keys isn't known in advance, you obviously have to prepare for collisions to occur. They are inevitable, and you can't prevent them from occurring because you don't control who calls the insert function and which keys they insert. Therefore, we have to define some scheme to resolve collisions. We call this a collision resolution scheme. And there are basically two broad categories of collision resolution scheme. What they come down to is either we allow multiple keys to share one index of the table, we're going to talk about that one today in this lecture, or we say if there are two keys fighting for the same index, move one of them to a different index, and then provide some extra logic to go find it again if we need it later. So those are the two categories of collision resolution scheme. The one we're going to talk about today is simply allow multiple keys to share the same index of the table. And there's a pretty easy way of doing this. What we do is, instead of storing the key directly in the table, we just have each index of the table contain a linked list. And then we can just add as many things to that list as we want. Anything that ends up hashed to index 4 of my table just gets thrown into this linked list. I'm actually going to, I know I'm going to say this. I'd like to avoid it, but I'm going to say it anyway. I tend to call these things buckets. So because it's a linked list, I can now throw as many things into index 4 as I want. And so you'll hear me say in this lecture, I'm going to talk about the things that end up in bucket 4. I tried to train myself not to call them buckets, but after years and years of doing that, so I wanted to call them something more sophisticated, like lists, or the things in index 4, but it's not happening. I'm going to call it a bucket. Throw your element into bucket number 4, and the bucket here is implemented by a linked list. When I first saw chaining on hash tables, I thought it was incredibly elegant. And actually, I thought chaining was much more elegant than the alternative approach that we'll see in the next lecture. But it turns out that because linked lists tend to be rather slow, in a constant time sense, the approach we're going to see in the next lecture is actually more likely to be used in a lot of cases. But for the sake of introducing ourselves to hash tables, I think chaining is the best thing to start with. Now, I keep saying the word chaining, and I just realized I haven't defined it yet. So this collision resolution strategy is called chaining, maybe for obvious reasons, because now each index of the table is the beginning of a chain of elements, a bucket full of different elements that are chained together. What's nice about it is it allows an unlimited number of things to share the same index. So even if our hash function does a bad job and we end up having a lot of things that get stuck into bucket number 4, I'll never worry about my hash table failing. I can always just string along more and more elements into a particular index. Now, that's a bit tough because it would be sort of nice if the hash table failed in that case so that we know as a diagnostic procedure that our hash function is doing a bad job. But certainly, since collisions are inevitable, it's nice to have this guarantee that no matter how many collisions occur, we'll always be able to store all the elements we want in our table. It is, of course, up to you if you design a hash table to investigate the behavior of your hash function. And a lot of the things I want to say in these two lectures about the behavior of hash tables, like how fast they are and how long it takes to use them in practice, I'm not going to actually show you any experimental results because I intend to assign exercises where you generate those results yourself. And that's what you should do when you design hashing functions and hash tables, is you should do experimental analysis to verify that everything seems to be working as expected. One thing we want, ideally in a hash table, is if we use chaining, it might be the case that some buckets have 2 things in them and some buckets have 0 things, but ideally we want the average size of buckets to be pretty consistent. I don't want to have one bucket with tons of stuff and every other bucket empty. Okay, so to insert something into a table using chaining, I have two steps. First, I evaluate the hash function. So suppose I end up, I guess I keep using bucket number 4. I end up in bucket 4, and then go into that and just insert the key into that linked list. And because linked list insertion is constant time, and under the reasonable assumption that our hash function can be evaluated in constant time, the insertion itself can be constant. Although we'll see later, there is a situation where the insertion might take longer because of a discretionary operation that turns out to be quite useful. Okay, so I'm going to do a quick example. I'm just going to scroll through these ones pretty quickly. Let's insert this sequence of values into this hash table using chaining and this hash function. Okay, so I insert 3, its hash value is 3, hash value of 14 is 5, 15 is 6. This is the same hash function as before where we just add together the 2 digits of the 2-digit number. We keep going. Eventually we end up with a collision. So we had 14 sitting in bucket number 5, and then I added key 5, whose hash code was also 5, and then we end up with 2 things in that list. And that's no big deal. And so we keep running through it, and eventually we end up with most of the table does contain, most of the indices of the table do contain a list of at least one element, and some of them contain 2 or 3, but they tend to be spread out reasonably evenly, which is pretty good. We're going to see shortly that actually, generally speaking, it's better to have a table that's a bit bigger for this number of items, that it's useful to have some empty space in your table. And in general, if your hash function is doing a good job, the bigger your table is, the smaller the lists are going to be inside of each bucket. And therefore, if you make the hash table bigger, you tend to decrease the size of the lists and therefore reduce the time it takes to search them. So speaking of searching, if I want to search a hash table, what I end up doing is basically linear search over one of the buckets. So if I'm searching for key K, I figure out what the hash value of K is. Let's say it's number 5, because that looks like the most exciting search case in the current example. Once I know which hash code I'm working with, I just perform linear search over the linked list in the bucket. Now, an interesting sort of tangent that I'm not going to get into, but to think about is, well, wait a minute, linear search is slow. Couldn't I make a hash table where each bucket was represented by something other than a linked list, a more complicated structure like a binary search tree or something? Well, the answer is technically, well, yes, of course you could try that, but in practice we don't do that because the reasons we use hash tables are because of simplicity, because we want to do very simple operations, simple, fast, streamlined operations. If we're going to make a bunch of binary search trees, it's not really worth it usually. Generally, then we would just use a binary search tree for everything. Anyway, so if I wanted to search for the key 87, which has hash code 5, I would first evaluate the hash function, and then I would search the contents of that list. And notice that the search itself is not constant time, because the size of the bucket could vary and could be dependent on the number of keys in the collection. And that's a bit dangerous. That's sort of a sign of a bit of a hazard. And so the question we should ask then is, what is the worst case running time of find if we use a hash table with chaining? And to answer that question, I'm going to do a different example. Let's insert this sequence of keys into this hash table. Okay, there they are. The first one was 13 with hash code 4. Second one was 68 with hash code 4. Well, that's a nasty coincidence. Now we have a collision. The third one was 4 with hash code 4. Okay, that's a bit awkward. The fourth one is 22. Okay, now this is getting a little bit weird. And the fifth one is 59. Okay, so every single key ended up in the same bucket. And that means that if I go searching inside of bucket 4, if I do an unsuccessful search, so that means I have to look at everything, then I've actually had to look at n things. My entire collection is in bucket 4. And this is the same kind of worst case result as we saw with binary search trees. So recall the worst case of a non-self-balancing binary search tree would be a tree that just sort of leans all the way to the left or all the way to the right, or even a tree that might go a zigzag tree that goes left, right, or something. In that case, we get none of the benefits of the clever search structure and all of the cost. So here I have a hash table. I've got all this extra machinery. I've got a hash function. I've got an array full of linked lists. But ultimately, I'm just doing linear search over a list. And that means that the worst case running time of find is linear. Because in general, we know that collisions are possible, and because the number of possible keys is so much larger than the set of keys that I'm actually going to store, it's reasonable that somebody could go picking through all the keys in the universe and just pick out a sequence of n keys that all map to the same index of my table. So it's quite feasible that I could end up with a table with only one index with anything in it, and that index contains n things. And therefore, find is big theta of n. It's linear in the worst case when the table already contains n keys. So if I go searching in this bucket and the thing I'm looking for isn't in it, I have to look at every single element before I can end my search, and that's going to be a big theta of n operation. So, okay, that's a bit disappointing, but what do we do? So what's the point of hash tables then? So remember a minute ago I said that the purpose of hash tables, the philosophy behind hash tables, is to get high performance via streamlined, clean operations. And way earlier in this lecture, I pointed out that there are certain compromises I might be willing to make. Maybe I will allow linear time find operations to occur in the worst case, as long as you can guarantee me that that worst case is extraordinarily unlikely. And also if you can guarantee me that in an average situation, so for a typical input, the search time is going to be incredibly fast. So that is, if you could show me that the search time was typically log n, but occasionally n, I wouldn't be interested. Then I would just go use a red-black tree. But if you can guarantee me that the search time is constant in almost every case and only linear in very, very unlikely cases, well, now I'm listening. So the question is, can we make that worst case really unlikely? And I want to show enough of a proof of this to give us the flavor of why this is a useful technique. Although it's true that one of the things we really should be proving isn't just the expected case running time of the find operation, but certain probabilistic results, I guess, on how likely the worst case truly is. And we're not going to prove those because not only are they a bit of a chore, but some of the probability that they require is stuff that may not be in your background. It's the kind of thing you would see in a higher level course on maybe randomized algorithms or probability in computing, or maybe algorithm analysis. So basically, what we know already is that collisions are inevitable. And therefore, we should expect in a typical hash table, there will be a couple of collisions. I don't know whether this is really that big of a problem, though. Having one or two things in each bucket isn't a big deal. If I could, hypothetically at least, guarantee that every bucket always had size at most 5, no matter how big your table was or how many elements you had, no bucket ever has more than 5 things in it. Well, if that were the case, then certainly searching would always be constant, because I just get into a bucket and I look at most 5 things. Of course, I can't make that guarantee. What I'm hoping to do instead is to make a sort of, is to prove something about the average size of a bucket that shows you that in a typical search, you can expect to only look at a constant number of things. So collisions themselves aren't actually a problem. It's no big deal if 2 things end up in the same bucket, or 3 things or whatever. I just want to avoid this catastrophic series of collisions that results in all n things in my collection being in the same bucket. Or, I guess more generally, I don't want to have 4 buckets that each have n over 4 things, or something. I don't want the number of things in a bucket to be some factor, some function of n, something like 0.5 or 0.1 times n. I want it to be ideally some constant, or I want it to be bounded by some lesser function of n, like maybe log n or something. So the problem with this is that part of this is the hash function's fault. So it actually turns out that although this distribution isn't that bad, this is actually a terrible hash function. And we want to define what a good hash function is, but it's very difficult to prove that a hash function is good, although it is pretty easy in many cases to prove that a hash function is bad. So we can prove that this hash function I'm using here, I've changed hash functions in the past couple of slides, this hash function turns out to be bad. And we can do that by showing that it actually never maps any key, no matter what integer you choose, 2-digit, 5-digit, whatever, it will never map literally anything to an odd number. So we'll never use any of the odd indices of my table. And that's obviously no good. What's the point of having all those indices if we're never, ever going to use them? Which means the reason everything ended up in an even numbered bucket isn't because I chose the input carefully. It's just because in every input, you're always going to throw every element into an even numbered bucket. So we know that this is a bad hash function. But the question is, okay, what makes a hash function good? And also, how do we show that? And strangely, although we can define what we think a good hash function is, it's very difficult and often not really worth it to go prove that a function actually meets that criteria. Instead, we know what a good hash function should look like. We know how it should behave. And because often we're designing hash functions based on specific data types, so strings or employee records or whatever, things that it's very difficult to mathematically prove anything about all strings or especially all employee records or all instances of some arbitrary data type. Even if we could prove properties of the data type, we can't really understand in advance the distribution of possible keys, the probability distribution from which a typical input would be drawn. And as a result, it may not be worth it to actually prove formally things about hash functions. Instead, we design hash functions with the idealized goals in mind, and then use maybe experimental analysis to verify that they seem to be at least close to achieving those goals. So we're going to make some realistic assumptions about what a good hash function looks like. Although the assumptions are realistic, they are sort of idealized. They're not the kind of thing that we can easily realize in practice. They're realistic because they describe what we expect out of a table that has a good distribution, and we expect that such functions exist, not that they're easy for us to produce. And the big assumption we're going to make is what I'm going to call the uniform hashing assumption. And I'm going to use a proper noun for that, so I'm going to capitalize it, because there are different ways we could phrase this assumption. If you go look at a book that talks about hash tables at this level, it will probably make some variant of this assumption, but it may not be phrased the same way. So I'm going to use it as a proper noun to make it clear that it's its own thing. It has its own identity as far as these slides are concerned. So suppose we have a hash table of size m, and our universe is called U, and suppose that H is a good hash function, whatever that means. In a sense, I'm defining it, but I'm saying H is a good hash function here, and we'll just leave the word good in the background for the time being. If H is a good hash function, then for any key selected uniformly at random from U, from the set of all possible keys, if I go into U and I randomly choose some key, the hash function is good if the probability that K hashes to any particular index is uniform, basically. In other words, if I choose some index, like 5 or 10 or 100 or whatever, the probability that a random key ends up at that index is just 1 over m. So in other words, if I choose a sequence of random indices, random keys, and I throw them into my hash function, I should expect that the probability of a collision is basically also just 1 over m. That is, the hash function is not biased towards any particular indices. Now, this is a result stated based on probabilities, and it has to be because, of course, if I choose a particular k, obviously that hash function is deterministic. So once I know the value of k, like if I discover that h of 5 equals 7, well, h of 5 will always equal 7. Once I know the value 5, the probability that h of 5 equals 7 is 1, because h of 5 always equals 7. This result is talking about the probability with respect to an unknown key. I've selected some key uniformly at random. I know nothing about that key. Before I use the hash function, I'm asserting that the probability that the hash function hashes it to some index I is 1 over m. Now, what this really means is that a good hash function is one that distributes keys uniformly, if I choose the keys randomly, among the different indices of the table. It isn't biased towards certain indices. This is usually considered a fundamental assumption to reason about the behavior of hash tables. And we can generally create hash functions that realize this to a pretty good extent. Proving that it's actually uniform is one thing. We don't generally need to do that. We just need to show, at least experimentally, that it achieves almost uniform performance to benefit from the advantages of having uniform hashing and the theoretical results we're going to see. So this is clearly a bad hash function because there are some indices that have a probability of 0. That is, the probability that any key gets hashed index 5 is fully 0. The hash function does not produce odd numbers. Therefore, this hash function would not be considered a good hash function under the terms of the uniform hashing assumption. As I said, in general, actually proving that it uniformly distributes keys is not easy, and it may not be worth it to do it, because not only does it require talking about all the possible keys that could exist, which is not easy if the keys are some strange compound data type, it also requires reasoning about the distribution of keys. Because if you think about, let's say you're making a hash table to store strings, the distribution of keys you're likely to see in that hash table is likely not uniform. It's not like we're going to select random strings to insert in a hash table. Most uses of a dictionary are on data with some kind of internal patterns, like English words or people's names. And I don't know how we can reason about the probability distribution of people's names. I mean, we could do that, I guess. We could look up a database of names and work out the probability of a particular name occurring or whatever. But that's way too much work for the kind of analysis we're trying to do. And also, writing that proof doesn't really give us anything because the proof is based on empirical data anyway, like a database of names. Instead, if we want to design our own hash function, function, maybe the best way to go about doing it is to make reasonable assumptions about our data, try designing a hash function, do some experiments, and refine our hash function as we go. And then do more experiments at the end to verify that the actual behavior we observe of the hash function seems to comply with uniformity. That should be enough to get the benefits of uniform hashing. And so keep that in mind, that although normally I'm very big on having a proof of everything, this is a domain where, because this is very data sensitive, having a proof may not even help us. And even if it did, it's a very hard thing to achieve anyway, especially on complicated, strange types of data. So all we need is to use this assumption to reason about the behavior of hash tables, and then design hash functions with this assumption in mind to try and achieve as close to uniform hashing as we possibly can. So any source you read about hash tables will state some variant of the uniform hashing assumption. They'll also talk about how an ideal hash function obeys this principle, although they phrase it differently. So because this is a topic that relies a lot on experimental stuff and empirical stuff, I did consult a lot of different sources while making these slides to try and create something consistent. And I found that although this is a very common precept, not everybody has stated it the same way. Some people state it sort of as an afterthought, like an obvious thing that anybody should be assuming. Some people state it as like they actually have a whole section about it. I have decided I will call this the scattering principle. That's a name I've made up because I need a name for this. And it talks about an ideal hash function. And I use the word ideal because I want it to be clear. It's not something I actually expect us to attain. I just want to state what I think would be a perfect situation. So in the ideal case, the output of our hash function should be indistinguishable from random data. So if I feed in a bunch of different keys, so I guess what I'm saying is, suppose I have my keys K1, K2, all the way up to Kn, and I run those all through H, and I get H of K1, and I get H of K2, and so on. What I'm really saying with the scattering principle is that if I look at all of these H's, if I look at the hash value coming out of the hash function for every key that I was working with, no matter which keys they were, even if I chose them deliberately to try and cause trouble, I want the hash codes to look basically like random data. In other words, if there was some pattern in the keys, for example, they were all even numbers, or they were all multiples of 17, or they were all English last names, or they were all student numbers at this university. Even if the data has some pattern, I want the hash codes that come out to be essentially indistinguishable from random data. So if I make some predictable change to a word, so if I take this last name here and I write it in lowercase instead, and I run that through my hash function, a minor change to the key that is thematically creates a thematic pattern, so I've just gone from uppercase B to lowercase b, should result in a change to the hash code that is completely random in a sense. Now, not really random, because of course the hash function is a deterministic function. If I feed in the same key more than once, I will still get the same hash code every time. What I mean essentially is that when I look at the hash codes for a particular sequence of data, I shouldn't be able to see any pattern in the hash codes that reflects a pattern in the original data. What this is actually saying, and this is a topic far above the level of this course, really what I'm saying is that I want the hash function to behave like what's called a pseudo-random number generator. That is, the data it generates seems almost random by a certain standard of randomness. This is the kind of thing that you'd learn about if you took a course on cryptography. And the uses of hash functions that are that meet certain cryptographic standards is of course important in cryptography, hence the word cryptographic, and also anywhere else you might use the word crypto. And there are a lot of places these days where you might use it. Hash functions play an absolutely massive role in crypto things, to the extent, frankly, that it's only a matter of the adoption of terms that we call things cryptocurrencies versus, let's say, hash currencies, because to a certain extent, they owe a lot more to hashing than they do to cryptography. So our scattering principle is, in the ideal case, the hash function should make such a complete mess of the key that you can't even figure out, if you look at the hash code that comes out, which key it went with. If I give you a set of keys and I give you their hash codes and I tell you match up each key with its hash code, you should be able to do no better than random chance at doing that matching. Now, that's an idealized hash function. We can't generally use that, and frankly, there are cases where we can define cryptographically secure hash functions or whatever, but using them for a hash table would be unnecessary. unnecessary. They'd take too long to evaluate. It would sort of be overkill. But if ever we can realize this principle or work towards it, we should strive to do so. Okay, here is the key claim, one of the two key theoretical things from this lecture. Under the uniform hashing assumption, the expected size of the list at each index of the table is n over m. And actually, this claim in some ways is almost trivial. That is, this actually applies in the most basic sense, even if our hash function is the worst possible function in the world. There are certain aspects of this that actually can apply if we tweak certain bits of the wording, even if we have a bad hash function. And there are certain ways I could write the proof for this that are way easier than the proof I'm about to show you. But I have an ulterior motive, which is that I want to set up some exercises for later, and I want to show off a pattern for a proof that can be easily adapted. So the claim is basically this, and I'll read in some intuitive meaning to it as well. If we have uniform hashing, then if I go and look at the list at any position in my table after inserting a random assortment of keys, so I select a bunch of keys randomly and I insert them into my table, and I go and look at the list at any position, I expect that that list will have this size. That is the expected size of that list. We could say, the word expected, of course, is a more sophisticated way of saying average, so I could say the average size of the list. But I really want this to be interpreted in a sense of, I mean that in the most intuitively deep sense of that. I don't just mean that I can show that the average size is n over m, because that's actually relatively easy. I mean that if we interpret the size of each list as a random variable, it has expected value n over m, and that the probability that it actually is near n over m is very high, although I can't prove that latter result today. There are results, and in the sources that I've used for this, which are in the slide, if you're looking at the slide deck that you've downloaded yourself, the last slide of the lecture has a list of sources. I'll put the sources in the description of the video as well. There are proofs that not only is the expected size of the list n over m, but the probability that the size of each list is near n over m is very high. So for now, I'll just prove this claim here. Okay, now as far as proving it, what I could observe is that there is actually a sort of dead easy proof, which is that if I add up the size of every list, the total number of elements has to be n. And the number of lists is m, which means that the average size of a list actually is n over m. And that actually is a valid proof. I could write that. I'm not going to. For some reason, I'm going to write this long probability-based proof. As I said, this is because that way I can assign exercises later that require variations on this proof, which can be easily adapted. Okay, so my justification is this. Let's take a random assortment, a random sequence of keys. So we'll do a sequence of random insertions of keys in U. And then I'm going to define a bunch of indicator variables. And so I have my keys. I'm going to use the index I to refer to different keys. And I have the indices of the table, which I will use J for. And what I want to think about is, let's think about a series of different events. So then these events could occur or not occur. Let's think about the event where key Ki ends up hashed to index J of the table. I'm going to define this variable xij to refer to the outcome of that event, whether it happened or didn't. So xij equals 1 in the event where ki hashes to index j, and it equals 0 otherwise. And you can verify that if I add up for all possible values of j, so if I take a particular value of I, let's do I equals 7 here, and I add up x7j for all values of j, that should equal 1, because each value k gets hashed to exactly one value of the table. However, I don't know what that value is going to be in advance, so I can define, because the values of the keys k are random, I can define a random variable to refer to each of the separate things that each ki could be hashed to. Okay, so under the uniform hashing assumption, I know that the probability that a randomly selected element ends up at a particular index is 1 over m. So the probability that each xij, for all I and j, is equal to 1 is just the probability that h of ki equals j, which is just 1 over m. Okay, so keep this in mind for the next slide. Okay, now what I want to do is come up with an expression for the expected size of the list at each position in the table. And so I'll call that list Lj, and I'll call its size Kj. Now Kj is a random variable because the keys I'm inserting are random. So what I can do is verify that Kj will just be the sum of all the x's for that particular j. So x1j, x2j, all the way up to xnj. That means the expected size of the list is the expected value of kj, which is the expected value of this sum. And by linearity of expectation, that would be the sum of these expected values. Okay, so now working backwards a bit, what is the expected value of any particular xij? Well, I can go and compute that because I can compute that very easily because xij only has two outcomes, 1 and 0. So the expected value would be 1 times the probability of it being 1 plus 0 times the probability of it being 0. And we know, okay, well, this is being multiplied by 0, so it's just irrelevant to me. I don't even bother computing that probability, although I could if I wanted to. So it turns out that the expected value just equals this, and we remember from the previous slide that this is 1 over m. Okay, so the expected size of Lj is n over m. Now, as I said, if all we wanted to prove was that, there actually is a much simpler proof that's about a paragraph long. I wanted to show off this method of proof, which I believe you've seen before, because in your background you should know about indicator random variables, because if I wanted to assess situations where, for example, there was a bias, I didn't have uniform hashing, I could use the same format of proof for that, for figuring out the expected size of the list under a situation where some indices are more likely than others, where I don't have uniform hashing. A related result that I'm not going to prove today because it requires more advanced probability that we don't have that you might see in a randomized algorithms course is not only is the expected size of the list n over m, but the probability that it's close to that number is very high. That is, it's extremely unlikely that a list is going to be too much larger than n over m, which is a pretty big deal. Now, the reason that it's a big deal is if the expected size of the list is n over m, that allows us to say that the expected running time of a find operation is related to n over m. For technical reasons that we don't need to worry too much about right now, I'm only going to refer to the expected running time of an unsuccessful find operation. Because we're not doing worst case analysis here, and that means if I want to talk about the expected running time of any find operation, I have to do a bunch of other algebra to work out the expected running time of a successful find. Because a successful find operation could take less time than an unsuccessful one, and I can't assume that's n over m. So to get around that, basically, to avoid doing that homework, what I will observe is clearly a successful search will be faster than an unsuccessful one. And so if I can show that an unsuccessful one is this long in the expected case, then a successful one might be better, but it's not going to be worse. So that means that if I'm bounding the expected performance above by this number. Okay, so the expected running time of an unsuccessful find is n over m. And that's a very interesting expression for a running time. We have a running time expressed in terms of a ratio, n over m. And we haven't seen that before, but there's something else about it that's pretty interesting, which is that one of the variables is under our control. We can't control how many keys get inserted into our dictionary, obviously. That's up to whoever uses the dictionary. But m is the size of our table. We are allowed to control the size of the table. In fact, we could change it whenever we want. If I decide that this table is getting too full, this table of size 8, what I could do is make a new table of a larger size. I could just make a table of size 15 or 100 or 1,000. And then I would, of course, have to change my hash function. So this hash function will be changed to be, let's say, mod 100 instead of mod 7. Although I think the table, it should have been mod 8, but I guess it was mod 7. That doesn't really hurt anything, although maybe index 7 becomes useless in that case. If I change my hash function to be mod 100 for a table of size 100, then I do have to take all my elements and rehash them to insert them into the new table. But I am allowed to do that. If I want to resize my table, I can resize it whenever I want. I just have to do the linear time resize operation followed by a bunch of bookkeeping, which takes linear time. What this means, though, is that I am in control of the running time of find. If I am in control of m, if I can change it whenever I want, I could configure m to always be just the right size to ensure that big theta of n over m is actually constant. For example, if I set m to always equal 2 times n, or to never be greater than or equal to 2 times n, then I'm guaranteeing that n over m will just be a constant, because m, of course, is defined based on n. And so by having this control, I can actually force the expected running time of find to be constant, as long as I keep track of m and make sure to resize the table as it gets too full. And that's a really big deal because we saw that the worst case of find was linear. But in this case, if I can guarantee that the expected case is always going to be constant by keeping m close to n, then I can expect that most searches will be extremely fast. It turns out the ratio n over m is important enough that it deserves to get its own name. We typically refer to it by the variable alpha, and it's called the load factor of the table. The number of things in the table divided by its size. And hopefully it's clear why it's called load factor just from this definition, but it's certainly a little bit less intuitive with chaining as with the other collision resolution scheme that we're going to see in the next lecture. So load factor makes a lot more sense in the next lecture than it does in this one. So here's some advice, a rule of thumb when you're implementing hash tables. Try to keep alpha around 0.6 or maybe 0.5. Generally, it's good to have empty space in your table because then your hash function can do a better job of spreading things out. It's good for there to be a bit of air to work with. It's not good to have too much empty space. I mean, if alpha is 0.1, you will get faster find times overall, but you're wasting a decent amount of space. It is a lot of empirical analysis has been done that has shown that although yes, 0.1 would give you faster performance, you're sort of into the law of diminishing returns at that point. Keeping it around 0.5 or 0.6 is enough to ensure that values get spread out reasonably well and that you do get that constant time expected find running time. Okay, so where does that leave us? Now we're at this table that I went looking for somewhere around slide 5 and couldn't find. Here are various dictionary implementations we've seen so far. If we have a hash function that provides us uniform hashing, or at least something reasonably close to it, we get a dictionary that gives us expected case constant insert, find, and remove, and worst case linear. Although, as I said, there are results that can be proven that show that that worst case is very unlikely. And we'll see later in this lecture more ways to make that worst case very hard to achieve. So even if I find a worst case input, there are ways I can ensure that next time I create a hash table, that worst case input will no longer be a worst case input. I can exploit certain randomness properties to make it so that even if you find a worst case input, it's only going to be valid for a short period of time. A few notes on the worst case situation. So in implementations where I may need to resize the table, so in cases where I want to keep m at some constant multiple of n, that means that on an insertion, if the table gets a little bit too full, I have to resize it. When I resize the table, I make a new table, which already takes extra time. Then I have to rehash all of my elements because the hash function will change given the new table size. And that's going to take linear time overall. So adding all of my elements back to my hash table will take linear time. If I don't resize the hash table, so in cases where I have a fixed table size, like I set it in advance because I know how big it's going to need to be, in those cases, insertion is actually worst case constant because if I use chaining to resolve collisions, all I have to do to insert something is find the hash code and then add something to a linked list, let's say at the beginning or end, which is a constant time operation. The remove operation requires performing a search because I have to go find the key I'm removing before I perform the removal. Now, in the expected case, search is constant time, and deleting a node from a list is constant time as well once you have the node. The problem is in the worst case, the search operation is linear, although deleting the node is still constant, but that means that remove is linear in the worst case. And as we saw, unfortunately, there are still cases, even if they're unlikely, where all of my keys end up at the same index, or at least some fraction of n keys end up at the same index, and that means that find and remove are linear. So an example here is, here's my hash function from earlier. Let's assume, even though I think there might have been a typo that should have said mod 8 there, let's assume it is mod 7 because that's how it's written. The exercise is find 16 values in the range 0 through 100, which are all hashed to the same index by this function. I don't suggest that you sit down and do this with paper and pencil. I mean, you could, and maybe if you know a lot about number theory or modular arithmetic, you could do that. I suggest write yourself a few lines of Python. Writing a quick loop in Python that just iterates over the numbers 0 through 100 would do pretty well as far as solving this exercise, and it's a useful thing to try out. It doesn't matter which index, it's up to you, whichever index is convenient, but find 16 values in that range that are all hashed to the same index. One thing that's worth considering if we take this as being mod 7 is that actually 16 is sort of if there being 16 collisions at a particular index between 0 and 100 isn't really that bad. Because if I'm going mod 7, there are only 7 possible output values, 7 possible indices. And that means that if I think about it, like what's 100 divided by 7? It's sort of it's nearby to 14 or 15 or 16. That isn't really that far off. This actually doesn't mean the hash function is that bad, but we should be aware collisions are possible and they're inevitable. All right, so here's my observation about the worst cases again. So I've mentioned, after all this time obsessing over worst case, I have mentioned here's a situation where maybe I can't turn this deal is too good to turn down. If I'm getting constant time, expected search time, and insert and remove, maybe I'll take that deal. But I still want to be mindful of worst cases, because we've seen other cases where an algorithm in the past has been pretty good in the expected case, like quicksort, but I still didn't want to use it because of its worst case complexity. Before I take this deal, I want to be absolutely certain that I'm protected against the worst case in whatever extent I can. That is, although yes, the worst case could occur, I want it to be absolutely unlikely. I want it to be so unlikely that I may never see it. And so what I can observe is, once I have a hash function, so that was the purpose of this exercise, if I give you this hash function, you can go and find me a long sequence of collisions. And so if we view running time as some sort of adversarial game where I make a data structure and you try and break it, if I show you my hash table and you see the hash function, you could walk away, find a sequence of collisions, and then feed them into my dictionary as a worst case input for linear time performance. I want to avoid that. But the problem is, once the hash function is known, somebody could always construct a worst case sequence of keys using that hash function. They could reverse engineer it, even if it takes them time, even if they have to go and use some computational time to do it. Interestingly, if you want to get into the crypto business or do crypto stuff, it actually turns out that a lot of the underlying technology behind blockchains and cryptocurrencies in fact relies on the idea that reverse engineering collisions in hash functions can be extremely difficult computationally. That is, the fact that such a huge percentage of the world's electricity has gone into crypto mining over the past 20 years has to do with the fact that finding collisions in certain hash functions is known to be computationally very difficult, or it's understood to be computationally very difficult. We actually haven't been able to formally prove that yet. It just doesn't seem to be an easily solvable problem. So once I know a hash function, even if it takes time, somebody could walk away, find a bunch of collisions, and then bring them back and use them and produce a worst case input. But now I think, wait a minute, do I have to use the same hash function every time? What I could do is, if I know you're going to go and try and create worst case inputs, or if I'm just worried that I'm processing the same data set over and over again, and maybe it happens to be a worst case input, what I could do is choose a different hash function every time I create a hash table. If I use a different hash function every time, what are the odds that the worst case input you come up with today is going to be the same worst case input for my hash function tomorrow? And I literally mean, what are the odds? What is the probability of that happening? I'll bet it's low. And so that leads us to an idea called universal hashing. And it's interesting because universal hashing also gives us a clever trick that allows us to achieve, for the most part, the benefits of our uniform hashing assumption. So I'm going to claim in the slides, I'm generally careful what I put in writing, I'm going to claim in the slides that by using universal hashing, we basically get a hash function on average that gives us the benefits of uniform hashing, of our uniform hashing assumption. There are a couple of asterisks attached to that. So if you're watching this while simultaneously taking some, high-level, graduate-level probability theory course or a randomized algorithms course, then yes, there are a couple of little asterisks that I'm not getting into here. But I think for our purposes, what I'm about to say is reasonable. That is, the function we end up getting out of this process is something that gives us the benefits of uniform hashing, if we also exploit what's called universal hashing. So it works like this. Suppose I have a collection of different hash functions. And of course, this is already, I can see why you might chafe at this when you think about choosing hash functions for your hash table. How do you have a set full of functions for this purpose? That sounds complicated. So bear with me. Suppose H is a set full of different hash functions. Often in this context, when we talk about these things, the functions in the set are variations on a theme. That is, they're not just a bunch of different functions somebody has designed from scratch. They're a bunch of related functions, and so we call them a family of hash functions. So suppose you have a family H of different hash functions. The family is called universal if, when I choose any two keys I want, so not randomly selected keys, like these are keys I could have chosen maliciously or adversarially, if for any two keys the number of functions in my family such that those two keys have a collision is at most the size of the family divided by m. Now, that's a weird definition to parse. What it's actually saying is, if I select a hash function uniformly at random from my family, the probability that any two keys collide is at most 1 over m, which is pretty good, because that means even if you found some clever collision for my hash function from yesterday, if I go and randomly select a new hash function today, the probability that your two keys collide today is no better than basically random chance, 1 over m. That's 1 over the total number of table indices, which is the probability of any random keys colliding under uniform hashing. And so what this means is if I have one of these universal families of hash functions on hand, and I randomly select a hash function every time I create a hash table using a random number generator or something, that means that my hash table will be pretty well insulated. It can defend pretty well against worst case inputs. Because what is the likelihood that a particular sequence you feed in happens to be a worst case input for a randomly selected hash function from this universal family? Probably very low. So even if you have a worst case input, it only applies for the hash function you're currently working with. So randomly selecting a hash function provides us quite a bit of defense against worst case situations, which is all the better if I'm trying to use a hash table based on its expected case performance. Now, here's a theorem I cannot prove because it requires, if I could ever prove it long ago as a student, I'm a bit rusty now, and it certainly requires number theory that we don't have in our background. So I won't give a proof of this. However, a proof can be found in the sources that I've put under the video and in the last slide of the posted slides. So actually, I think now that I think about it, the proof isn't that advanced in the number theory, but it does require number theory that we don't have, so let's not worry about it. Suppose I have a universe of possible keys, and I have got some value m, which is the size of my table, and let p be a prime number with this property. So p is a prime number between the size of u and 2 times the size of u. The existence of such a thing is guaranteed. So if I look at there will always be a prime number between something and 2 times that thing, as long as I have one end of this inequality be inclusive. So I'm allowed to actually have it be 2 times u, although ask yourself when that's going to happen. Or if I allow it to actually be the size of u itself, I guess. So now if I have, for any two values a, where a is between 1 and p minus 1, and b, where b is from 0 to p minus 1, define a function called HAB. And HAB is just this expression, a times the key plus b, all mod the prime number, and then mod the table size. I know it's weird to have 2 modulo operations in a row like this, but it's necessary because we need to make sure the result comes out to actually be less than m minus 1. Actually, the more I think about it, this really needs to be a less than or equal to sign there. So sorry about the typo. All right, so I've defined this collection of different functions, HAB, based on these values AB. Now let H, big H, be the set of all possible HABs for all the different choices of A and B. This family is universal, and the reason is due to some weird, spooky number theory stuff, so we're not going to write that proof ourselves. What's interesting about this is, first off, all of this about universal families and collections of hash functions doesn't really provide us much of a path to implementing anything, but this particular universal family is actually something we can use in practice. If I am creating a new hash table in my code and I want to randomly select a hash function, I could just use this HAB that we just described. All I do is generate a random value A and a random value B, and I use those as the coefficients for HAB. So it's actually relatively simple if I have a random number generator lying around to generate a random hash function. I just generate these 2 random parameters. So what the theorem tells us is that as long as I use one of these universal families, I can get the benefits of universal hashing and uniform hashing, and that's the place where there's a bit of an asterisk. There's certain situations in a higher level setting where if you wanted to write proofs or whatever, you'd have to be very careful about this claim, although for our purposes it is sound. So we can actually achieve that. We now have an example of a universal family, and as I said a minute ago, despite all of the other things, the fact that this means that your adversary can't find a lasting worst case input, we also get the fact that if you accidentally encounter a worst case input, so if your code is processing the same data over and over again, and it happens that on one occasion it's a worst case input, every time when you choose a new hash function, it's very unlikely that the same sequence will also be a worst case input for that. So I think that that's enough to show that we can really reduce the likelihood of that linear time worst case and benefit from the constant time expected case of find, insert, and remove. Now, we're not done talking about the structure of hash tables because we have to talk about a different collision resolution scheme. But I mean, I know my limit, and given the odyssey we've already been on today, we'll make that a separate lecture. I do want to finish off on one other example, though. I want to talk about designing a hash function for a data type that is not a bunch of integers. I want to talk about string hashing. So the task is design a hashing scheme to insert this collection of strings into this hash table. And these are strings of text, but I suppose we should assume that we're allowed to store strings of any characters we want. So let's say any 8-bit values. Now, the output of a hash function must be an integer. So in many cases, one of the challenges we face is finding a way of mapping non-integer data to integers. But in this case, we can leverage the fact that strings are generally stored as sequences of individual characters, and characters are just stored as numerical values. So I could just leverage the underlying encoding of characters as a way of computing a hash value. So that's what I'm going to do. That's the shortcut I'm going to use in this example. Now, I have to say this, but theoretically at least, the numerical value of a particular character in a computer doesn't have to be the same thing on every computer. So it happens to be that on every computer you are ever likely to see or use, the numerical value of lowercase a is 97, because we're using the ASCII character set. And that means that it is considered bad form in code that you write for any reason to assume that the numerical value of a is 97, because that character set is still arbitrary. Even though it is the one everybody uses, it is still arbitrary. So if you write code that assumes that a is 97, people are going to think that you're weird. They're going to think you don't know how to program properly. And you know what? That's a place where some judgment is actually sort of deserved. Just use your character constants. Don't assume that they're numbers, because people can read them more easily as well. However, in this example, because I'm going to do examples where I compute my hash code based on the numerical values of characters, I have to use some character encoding to come up with numbers, so I'll just use the one built into my computer. I'll use the ASCII encoding. But in general, when you do this, make sure you don't assume you're always using ASCII encodings unless you write conversion logic yourself. It's no different than when they tell you about little endian versus big endian numbers. Don't assume numbers are always stored in one or the other. Use code logic that only makes assumptions that are relevant to the specifics of the platform you're running on. And if you want to write cross-platform code, use library functions that provide information about byte ordering or reorder the bytes. Same thing with using ASCII or other character sets. But it is, frankly, the case, and I don't want to admit this to first-year programming students so much, but I will admit it to people taking an algorithms course. It is the case that if you really wanted to see a character encoding of 8-bit values that didn't use ASCII, you'd have to go to some computer museum or something. Like there aren't any machines you are likely to ever see or use actually in use that actually still function these days outside of a museum that use any other character set. Okay, so here's one idea. I could just take all the characters in my string, C1 through CK, add them all together, and then take the result mod 7. This is a good start, but it's a start, and it turns out this function is a pretty bad hash function. And I like this example, and I wanted to show this example because I want to document the process of how do I create a hash function from scratch, and like what is the feedback loop I want to realize? Like if I try something and it fails, what do I do about that failure, and how do I diagnose it? And often the answer is you do experiments. But at first you do, I guess, just some sort of cursory analysis on your own, like anecdotal analysis of data, just to see whether any of the patterns that show up look a bit hazardous. So let's try putting all of our strings in the table using this hash function. Okay, so the word ocean, I break that into 5 characters. These are their ASCII values here, and they sum up to 518. Take that mod 7 at 0. The word boat has these 4 characters. I add them up, I get 422. That goes to index 2. The word tide, oh, that's too bad. The word tide ended up in a collision with the word boat. Okay, so they ended up in index 2, but that's not a big deal. I shouldn't worry too much because there are always going to be collisions in a hashing scheme. The word sand, okay, that's a bit annoying. That also ended up in index 2. Now notice that the word tide and the word sand have no characters in common. It feels like this is just a sort of unfortunate coincidence. That is, they all add to 422, but their character codes are actually all different. They just sort of, some sort of weird constructive interference happens where they end up having the same sum. The word canoe ends up in index 0, and the word wave ends up at index 1. So I have a hash function that took 6 input strings and crammed them into 3 indices. That's not ideal. It would be good if the hash function distributed them better. On the other hand, the question we should be asking ourselves is, are there any patterns in the output that we can trace back into the input? Are there any reasons why this hash function, because maybe it's just had a bad day, like maybe we've given it a bad break with these strings. There are always going to be sets of inputs that any hash function will distribute this way. The question we should be asking is, to what extent can we ascribe this problem to a design flaw versus just bad luck? Okay, so is there an obvious cause for these three collisions? And the answer, I actually think, is no. I think it is sort of unpleasant. It's sort of a bizarre coincidence, but it doesn't seem as if there's anything inherently wrong with the hash function here. That is, the fact that all the letters in these two words are different is a sign that maybe it's just sort of bad luck that they all sum up to the same thing. It's true that if I use a different hash function, I might not have these collisions, but it doesn't mean that these collisions are the fault of the current hash function. What about this? So the problem with these two words is that they're anagrams. They contain the same letters. And that means that this is actually the hash function's fault. There's a pattern in the output. If I pass in two words that have the same letters, I will get the same hash code. So think about, and I could use this to engineer a set of collisions, and that's no good. That is the fault of the hash function. So suppose I try these 4 strings here. If I compute the sum of the character codes of the 4 letters in each of these strings, the sum will always be the same, because when I add up the character codes, of course, the order in which I compute a sum is irrelevant because the addition operation is commutative. And so that means these 4 things are guaranteed to always collide if I use this hash function. No matter what table size I'm using, no matter how long I make the strings, any 2 strings with the same sequence of letters in a different order will always have the same hash values. And so these collisions are definitely a design flaw in my hash function. And we can see, so the word ocean is 111, there's the 111 down there, plus 99, plus 101, plus 97, plus 110. So it's just the same terms in a different order. So they're guaranteed to always map to the same index, as are any pair of anagrams. That's a serious problem. And I'd say if we want to ascribe this to violating a specific principle, well, I don't know whether this hash function gives me uniform hashing or not. And I don't really want to look into that because that would require writing a bunch of proofs that require me to know things about the distribution of strings, which I don't know. But I can say this does seem to violate the scattering principle. The scattering principle, remember, was the one that said if I look at the hash codes that come out on a given sequence of inputs, I should not be able to ascribe any particular pattern in the hash codes to a pattern in the input. But I know now that if I pass in a bunch of anagrams, they're always going to have the same hash code. And that's a pattern that goes right through the hash function. And that means that anybody who knows about that could characterize the conditions for a collision and come up with a long sequence of colliding keys and create that worst case sequence. All right, let's try something else. So the problem is in the hash function. How do we fix it? Well, in general, like we saw at the very beginning when we work with the last digit of numbers, one way of making a hash function better, regardless of why it's bad, one way of making it better is incorporating more information about your key. So although we were using every character of the key, we weren't taking into account the position of each character. So my second try attempts to take that into account. It uses a weighted sum where I multiply each character by a power of 2 based on the position. So character 3 gets multiplied by 2 to the 3. Now actually it turns out in practice powers of 2 aren't the best for this. We might want to use powers of something else, but I figured powers of 2 are a good starting point. I'll talk more about that in a minute. Okay, so this new hash function weights each character based on the position of the character, and in so doing, the hash value will contain more information about the key, more of the information that was encoded into the string that I passed in. Okay, so ocean goes to bucket 2, boat goes to bucket 3. Oh, there was a collision. And hopefully it's clear this collision does seem to be more or less random chance, just bad luck. I mean, my table's only so big. There are going to be collisions, I can expect. And then everything else ends up in a bucket by itself. Does that mean this hash function is good? Well, okay, that's a bit too soon to say. It does mean this hash function seems to have averted the main problem of the previous example. If I want to know whether this hash function is good, I should try it again on many more inputs. I should try tons and tons of collections of the same number of strings. I should try it out on a larger collection of strings with a larger table. I should just run tons of experiments and analyze how many things end up in each bucket on average, and what the maximum size of each bucket is across all of my experiments. That's one way of validating the hash function, and it's way easier and likely more productive than if I were to try and perform some theoretical analysis, because there are too many theoretical questions here that I have no answer to that would prevent any theoretical analysis from being meaningful. So the keys are spread out more evenly. This could be luck, but we have some evidence now that we fixed one of the major problems in the previous example, and this gives us enough to go forward and start doing more experiments. And as we do more experiments, we might find more flaws to correct. So on the subject of string hashing, just so we can close that topic off, it turns out this style of hash function, this weighted sum where I use a power of some constant a to weight each term, that is actually pretty useful. And don't take it from me, because I haven't gone and done those experiments, but the authors of this book, and this is in the list of cited sources, apparently did a bunch of their own experiments and determined that for English text in ASCII characters, these values of a, 33, 37, 39, and 41, are really good for that. So there you go. And if you don't like that, take it up with them. And as I said, generally that is the best way to validate hashing of interesting exotic types of data, especially if you know that the use case of the dictionary is going to be using something other than literally randomly generated keys. We know that for string hashing, we're not going to be hashing random strings in most cases. We're going to be hashing strings that contain certain patterns. And the best way to assess the effectiveness of a hash function, therefore, is to evaluate it on strings containing those patterns. Just do experiments. And you wouldn't be surprised if you find me assigning a bunch of exercises involving doing just those experiments, because that is, I think, the easiest and most productive way to assess the effectiveness of a hash function. Now, we're not done talking about hashing, although the next lecture will be a bit less of an odyssey than this one. We still have to talk about another collision resolution strategy. We talked about chaining today, and chaining is great. It also makes it much easier for us to talk about certain theoretical aspects of hash tables. However, the need to use linked lists means that chaining is not an attractive option in certain practical cases. I keep referring to the Python dictionary, the dictionary used by the C Python implementation of the Python interpreter. It does not use chaining. It's a hash table, but it doesn't use chaining. So we'll find out what machinery it does use in the next lecture.